How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at some 15.1 through 3, the concept of equilibrium and the equilibrium concept. So our objectives will be to explain what an equilibrium is and what conditions must be met for it to exist, determine the proper equilibrium constant expression given a balanced chemical equation, calculate the value for KEQ given equilibrium values of reactants and products, infer if an equilibrium lies far to the left or to the right based on the magnitude of the KEQ constant, and manipulate equilibrium and determine the following value for KEQ. For example, if you flip the equation, what happens to the KEQ? So number one, at equilibrium, what's true at equilibrium? The chemical reactions have stopped. That is not true. So when we're talking about equilibrium, there's still a forward process, but there's also a reverse process that is at the same speed. It's like running on a treadmill. You crank up the speed, you also got to run faster. Overall, you're not going anywhere. So not A. The equilibrium constant is 0. That is not true. The limiting reagent has been used up. That is also not true. The rate constants for the forward and reverse reactions are equal. Maybe let's see E. The rates of the forward and reverse reactions are equal. So it's definitely going to be this right there. The rates of the forward and reverse reactions are equal at equilibrium. 2, what does the Haber process produce? So the Haber process is you take nitrogen, N2 gas, which is in the atmosphere and abundant, and you add H2 gas to it so that you can end up making NH3, which is ammonia, right? This is a important chemical compound for things like fertilizers and such. So that is the Haber process. 3, which one of the following will change the value of an equilibrium constant? All right, well, adding inert substances that are not involved in the equilibrium, that's not going to affect the equilibrium at all. It's not involved. It tells you right there. It's not involved in the equilibrium, will have no effect. Changing the temperature, yeah, that will affect the equilibrium constant. If you change the temperature, you change the constant. What about C? Changing the initial concentrations of products? No, that won't affect the equilibrium constant. You'll still end up at the same equilibrium. Changing the initial concentration reactants? Nope, for the same reason. Changing the volume of the reaction container? No. So B. All right, 4, what is the equilibrium constant expression for the following equilibrium between dinitrogen tetroxide and nitrogen dioxide? So we know A, the equilibrium constant expression is going to be equal to the concentration of the products to whatever their coefficients are over the concentration of the reactants to whatever the coefficients are for that. So here I go, all right, what are my products? I got NO2. So what is the concentration of NO2? And its coefficient is a 2, so it's going to be to the second power, divided by the concentration of the reactants. So concentration of N2O4 to the, well, hey, there's no number written there, so I know it's to the 1. You could write the 1, you don't have to, but that's the equilibrium constant expression for that equilibrium. What is the equilibrium constant expression for this equilibrium? So again, it's going to be products over reactants. So we only have one product. So it's going to be the concentration of CH3OH over the concentration of the reactants. So I got CO2, and it had a coefficient of 1, so I'd just leave it as that. And then H2, and it has a coefficient of 2, so it becomes the exponent. And that's the equilibrium constant expression for that one. Also, I want to point out the double arrows here is indicating that there's a forward process and a reverse process. Sometimes you might see them as like 2 full arrows, or sometimes you'll see like kind of half an arrow. They're both saying the same thing. All right, 5, the Kp expression for the reaction below is, this P is for pressure. So it's the same thing, but instead of the concentrations, you use the pressure of the products over the pressure of the reactants. And then again, to whatever power the coefficients are. So here the product is O2 gas. So it's going to be the pressure of O2 gas to the third power because of this 3, divided by the pressure of O3 gas to the second power because of its coefficient of 2. That's the only difference in the expressions. All right, given the equilibrium below, equilibrium cannot be reached when blank is placed in a closed container. So first off, it needs to be a closed container if we're going to have an equilibrium, because all these things are gases and we have to trap them in together. So in order for an equilibrium to occur, we need a forward and a reverse process, which means we need to either start with all of the reactants or all of the products in order to have both processes possible, right? If I just had N2, there's no way I can go forward if I didn't have O2. So that's going to be kind of what this question is testing. So let's take a look. Can it reach equilibrium if we started with 0.25 moles of NO2 and 0.25 moles of O2? Yes, we can get equilibrium because we have all of the reactants, which means we'll get a forward. We'll make this, which means then we can have a reverse reaction. All right, let's see option B. 0.25 moles of NO2 and 0.25 moles of NO3. Well, hey, we have all of the NO3 that we need so that we can go reverse, and then we'll make O2, which means, hey, now we can go forward as well. So second option, equilibrium can also be achieved. All right, what about C? 0.5 moles of O2. Here, let me clear my work, right? All right, we start with some O2 and 0.5 moles of NO3. Hey, I have all the products I need to give me the reverse reaction, which will make NO2 so I can get the forward reaction. Choice C can also create an equilibrium. All right, choice D, 0.75 moles of NO2. Hey, I don't have O2, which means I can't go forward to make NO3. I also don't have any NO3, so I can't go and reverse. So choice D will look the best. And then E, 0.1 moles of NO3. Hey, I have all of my product, which means I can do the reverse to make all my reactants to give me the forward. So choice D it is. All right, number 8, the equilibrium constant expression depends on the blank of the reaction. Does it depend on the amounts of reactants and products present originally? No, it doesn't. Does the equilibrium constant expression depend on both coefficients of the reactants and the mechanism? No, not quite. Does it depend on the coefficients of the reactants and products? Yeah, that is very much true. Does it depend on the mechanism? No. Does it depend on the temperature? No, because we're talking about the expression. The value will, what the number is, yeah, but the actual expression will not depend on the temperature. All right, number 9, the equilibrium constant for the reaction below, here it is KQ equals this number at a given temperature. At equilibrium, okay, so they're asking us to take a look at the value for this number, and it tells us that it's 10 to the minus 3. So we know in general, the KEQ has the products over the reactants. So if it's really big, that's a G. That tells us we got a lot of product, and if it's really small, that's telling us, hey, we have a lot of reactants. So this 10 to the minus 3 is a small number. At equilibrium, only products exist? No, that's not true. For any equilibrium, you got both. Only reactants exist? No. Products and reactants are equal? No. Right? There are more products than reactants? No. And there are more reactants than products? Yes, because if we had a small amount of product over a whole lot of reactants, that's how you end up with a tiny number, right? So choice E. Okay, number 10, the equilibrium constant for the reaction, here it is this number at a given temperature. At equilibrium, all right, same kind of question, but this time the number is different. We got 2.75 times 10 to the second power. So we know that both products and reactants have to exist at equilibrium. This one, products are equal to the reactants? No. All right, that's almost never going to be it. There are more products than reactants. Well, let's see, 10 to the 2 is a big number, so I'm going to say, yeah, we have a bigger number over a smaller number, products versus reactants. So we got more products than reactants, right? Number 11, the equilibrium constant for the reaction A is K. So we're saying, hey, this is K. What is it for B? In terms of K, what is the equilibrium constant for reaction B? Well, how did we go from A to B? Well, here we have NO3 as a product, and then in B we have Z as a reactant. So we had to flip it, right? So if I had K, how do I flip K? Well, K is really K over 1. So if I flip it, if I'm flipping reactants and my products, I got to flip K. So I end up with 1 over K. And then I also went from only having one NO3 to 2 NO3s, and you can see the same thing happened to the coefficients of the other stuff. We had 1 NO2, now we got 2. We have half an O2, now we have a full O2. So if we doubled the coefficients, remember that the coefficients became the exponents. So now the exponents get doubled, which means we square it. So it's really 1 over k squared. Or, you know, it's the same thing as saying 1 over k and then that whole thing gets squared. Either is acceptable, but this would be the answer. All right, 12. The value of KEQ for the following equilibrium is 598 at a given temperature. What is the value for KEQ for the following equilibrium? All right, so let's see. We start with H2 plus I2 gives me 2HI. And hey, all the coefficients were cut in half, right? If I were to write out the expression for this, you go, hey, products, HI, to the exponent, originally it was a 2, divided by H2 concentration times I2 concentration. And then, hey, what about this new one? Well, it would be HI to just the 1 power all over H2. Sorry, I decided I can't write. To the 1/2 times I2 to the 1/2 power. So how do we go from this to that? Well, easy. If we cut the coefficients in half, then we're taking the square root of k. So what's the square root of 598? I hope I did that already. 24.5. So that would be the value for that KEQ. 13, given the following reaction at equilibrium at 300 K, if PCO2 is 0.0225 atmospheres, what is the KC? All right, so there's a couple of ways to do this. If you wanted to convert KP to KEQ in terms of concentration, you can remember this equation. KP equals whatever the KEQ is times R times T to the change in N. This N is the change in how many moles of gas. So you can see the reactants we had 0. The products we have 1 mole of gas. So our delta N will equal a positive 1. So if I want KEQ, I go, all right, well, let me rearrange this. KEQ is going to equal KP divided by RT to the 1 power. So now I can just plug and chug. All right, the KP, well, hey, what is the KP expression for this reaction? It's just going to be equal to the pressure of the products, which is just CO2. The other one's a solid, so it's not involved. Divided by, hey, that's just a solid 2. So here the KP is the pressure of CO2. So all right, 0.0225 divided by RT to the 1. And then you end up with 0.000914. Another way to do it is you can go, hey, if I know the pressure of CO2, let me convert that to my molarity. You could pick a volume, you know, deal with 1 liter or something, and then go PV equals nRT, solve for N at like 1 liter, and that'll be your molarity. You can do it that way too. 14, the following reaction is at equilibrium. There it is. If the pressure of this is that and that, what is KP? So let's start with the expression. KP equals the pressure of the products. Well, here I got a gas, so the pressure of NH3 times the pressure of, well, H2 is also, or H2S is also a gas. So H2S divided by the pressure of the reactant. Since it's a solid, there is no pressure. All right, so we go, all right, well, let's see. It says pressure of NH3 is 0.605 atmospheres times the pressure of H2, which is the same value, 0.605. So when I plug those numbers in, the value I get is 0.366. So that would be my KP value. All right, I hope you found that helpful. See you in class. Okay, bye.